Hello everyone, I'm Chao Junrong. This course focuses on WDM systems and OTUs. Topics include the position of the WDM system within the entire communication network, composition and architecture of the WDM system, composition and signal flow of WDM devices, functions and categories of OTUs, and application scenarios of the WDM system. People often ask me where the WDM system stands in the entire communication network. Let's first look at two common networking diagrams. The first one is FBB. In this network, we can see from left to right are the access network, metro network, and IP core, all connected by optical fibers. The next is MBB. The backhaul core is on the left and the IP core is on the right, also connected by optical fibers. For LTE or LTE-A networks, the backhaul can be further divided into fronthaul and backhaul. Finally, let's look at an actual networking diagram. As shown in the diagram, devices on the FBB or MBB network must first be connected to WDM devices through optical interfaces before being connected to the actual line fibers through WDM devices. However, connections between devices in MBB and FBB networks are virtual, and the network design is only a logical design. You might be wondering, why do we have to use the WDM network? The longest transmission distance supported by optical interfaces on an SDH or router device is 80 kilometers. Additionally, the optical interfaces commonly use gray light, meaning that one optical interface occupies one pair of optical fibers. Therefore, in a backbone network, IP and SDH devices will encounter transmission distance and fiber resource limitations. Limited optical fiber resources are an especially common issue in metro networks. However, the WDM network can have 40, 80 or more channels in a single optical fiber, and each channel can transmit an optical signal, multiplying the transmission capacity by tens or hundreds of times. Furthermore, the WDM system uses the advanced modulation encoding scheme and the forward error correction algorithm, achieving transmission over thousands of kilometers without electrical regeneration, greatly reducing costs. In this figure, we can see that the WDM network can be divided into the backbone WDM network and the metro WDM network. Let's take a look at application scenarios for these two networks. Backbone WDM network application scenarios are separated into 5 types. The first type is the submarine cable system. Submarine cables mainly connect networks across continents or oceans, for example, between Europe and America. Some island countries also need submarine cables for transmission. The second type is the Pan-European trunk. The Pan-European trunk was specified as an application scenario because Europe contains many countries, most of which are developed countries. Many of our customers and worldwide Tier 1 operators are based in Europe and have well-established international networks there. This makes Europe one of our main subdivided scenarios. The third type is the Common International Network, also called the International Trunk. It usually crosses several countries and is constructed by one or multiple operators. The fourth and the fifth are both domestic trunks. Generally, there are a few levels such as national trunks, provincial trunks, state or regional trunks, depending on the country's size, economic conditions, and population. Next, let's look at the application scenarios of the metro network. The architecture of the metro WDM system is simple and includes the metro core network, metro aggregation network, and metro access network. In almost all developed and developing countries, WDM networks have been deployed in metro core networks. In some developed countries and all developing countries, the WDM system has been deployed at the metro aggregation layer. The metro aggregation layer connects the metro core sites and edge sites, such as CO sites, or BBU cloud sites. In some developed countries, such as Japan and South Korea, with well-developed LTE/LTEA networks, WDM devices have been deployed to the access layer and are directly connected to the RRU sites. This covers the architecture and application scenarios of backbone WDM and metro WDM networks. Next, let's take a look at the composition of WDM devices. Here is a simple example of a point-to-point network from Site A to Site B. A WDM device includes an OTU, a multiplexing/demultiplexing unit, and an amplifier. Let's see how a signal is processed in the WDM system. First, the optical signal from the client side enters the OTU of the WDM device. The OTU converts the gray signal from the client side into the colored signal specified by the WDM side. After the conversion, the specific wavelength enters the MUX/DMUX unit of the WDM system. The MUX/DMUX unit multiplexes and demultiplexes different wavelengths for different WDM system capacities. For example, for an 80 wavelength system, the MUX/DMUX unit multiplexes and demultiplexes 80 wavelengths. Multiplexed or demultiplexed signals are usually amplified through an optical amplifier before being transmitted through optical cables. The amplifier amplifies the optical signals so that the receive-end optical components are able to successfully receive the optical signals. The receive end also needs an amplifying unit to amplify the optical signals from a remote end. In addition to the aforementioned devices, an optical supervisory unit is required to manage and monitor the WDM system. Generally, the optical supervisory unit uses an independent wavelength outside the DWDM wavelength range. For example, in the DWDM system, we use the 30 nanometer range and the 1550 nanometer window. The supervisory channel uses the 1510 nanometer window to ensure that the supervisory channel will not affect surfaces on the main channel during transmission.